Today, we are diving into one of the most incredible stories in all of human history, how we went from counting on our fingers to building machines that can actually learn. This, right here, is the story of how we taught silicon to think.
So let me start by asking you a question. What do you think the very first computer was? You probably picture a massive machine with gears and levers, right? Or maybe something from World War II with blinking lights. Well, believe it or not, the answer is a person. Yeah, you heard that right. The word computer first shows up way back in 1613, and it wasn't a machine. It was a job title. A person's job was to be a computer, someone who performed calculations all day long. They were the original processing units.
So, to make that incredible leap from a human brain to a machine, any device had to tick three really important boxes. 1, it had to follow a specific set of instructions. 2, it had to be able to run through a pre-recorded list of those instructions on its own. And 3, it needed a way to quickly store and pull up a whole bunch of data. This was the blueprint, the DNA for every single computer that came after.
That need for a machine that could calculate kicks off our first era, the age of mechanical calculation. This was all driven by a basic human desire, a quest to get faster and more accurate than we could ever be with just our own brains and hands.
And this quest goes way, way back. We're talking about the abacus in 2400 BC. But what's really wild when you look at this timeline is the pace. Notice those huge gaps? For thousands of years, progress just crept along, and then bam! A sudden explosion of creativity in the 17th century gives us a bunch of new complex tools.
And you can see that acceleration right here. Pascaline was a huge deal, but it could only add and subtract. Just 30 years later, which is nothing in the grand scheme of things, Leibniz's stepped reckoner could do it all: add, subtract, multiply, and divide. That leap shows you just how fast the ambition for these machines was suddenly growing. But just doing math faster wasn't the endgame. The next great breakthrough wasn't really about calculation at all. It was about control. And this brings us to the dawn of programming, the moment we started to figure out how to actually teach these machines what to do. This is the pivot point in our entire story. The goal wasn't just to build a better calculator anymore. It was to build a machine that could follow a script, a set of pre-recorded instructions. That one idea, that changed everything.
And get this, the idea didn't come from a mathematician. It came from a textile factory. The Jacquard loom used cards with holes punched in them to tell the machine what pattern to weave. For the very first time, a machine was reading a stored set of instructions to perform a really complex automated task.
Now here's where that industrial idea gets a serious upgrade. A guy named Charles Babbage, who we often call the father of the computer, took that concept of stored instructions and applied it to math. His incredible design, the analytical engine, was basically the first blueprint for a general-purpose programmable computer, a machine you could actually tell what kind of problem to solve.
And Babbage didn't figure this out alone. A brilliant mathematician named Ada Byron, you might know her as Ada Lovelace, saw the true potential in his machine. She wrote extensive notes and algorithms for it, realizing it could do way more than just crunch numbers. It could manipulate any symbol. And in doing that, she effectively became the world's very first computer programmer.
That punched card idea from the loom? Well, it came roaring back decades later. Herman Hollerith's tabulating machine used those same cards to process all the data for the 1890 U.S. Census. A job that was supposed to take a decade was done in just 1 year. This was the proof, the absolute proof, that programming could solve massive, real-world data problems.
But there was a problem. Mechanical gears are slow. They're clunky. To get to the next level, we needed a new power source. We had to move away from physical cogs and into the world of near instantaneous speed. Welcome to the electronic revolution.
And two machines really marked this turning point. The Ada Berry computer was the first to use electricity for digital computing, but it could only do one job. The real monster breakthrough was ENIAC. It was the first general-purpose electronic computer, one machine that could be reprogrammed to solve all sorts of different problems.
And the difference between them? It was just staggering. Mechanical machines were slow, clunky, relying on physical parts grinding together. Electronic computers, using vacuum tubes to control the flow of electrons, were literally thousands of times faster. They were versatile, they were powerful, and they set the stage for everything that was to come.
Okay, so the next big step was making these incredible machines practical. UNIVAC I was the first computer you could actually buy commercially for a business. And then EDVAC introduced another game-changing idea, the stored program concept. This meant both the instructions and the data were held in the same memory. And that fundamental architecture is in virtually every computer you own today. Now, all of this incredible progress can be broken down into 5 distinct generations, each one defined by a major technological leap. This is the final leg of our journey, the lightning-fast race to make computers smaller, faster, and a whole lot smarter.
And here's the roadmap for that race. We start with vacuum tubes, then we jump to transistors, then to integrated circuits, then to microprocessors, and finally, we land right where we are today, in the age of artificial intelligence. So these first-generation computers, they were giants, absolute monsters. They used vacuum tubes for processing, took up entire rooms, and generated so much heat. They were also incredibly expensive and had to be programmed in the most basic, complex machine language. Powerful, sure, but a total nightmare to actually use.
And then came the invention that changed everything, the transistor. This tiny little device replaced those big, hot, unreliable vacuum tubes. And just like that, computers became smaller, faster, cheaper, and way, way more reliable than they'd ever been before.
To really understand the scale of this leap, just think about this number. One single tiny transistor replaced the equivalent of 40 of those enormous vacuum tubes, and it used just a tiny fraction of the power. It was a revolution.
The third generation was all about miniaturization, cramming tons of transistors onto a single silicon chip, the integrated circuit. This massive boost in power and efficiency made it possible to introduce things like keyboards and monitors. This is the moment when computers started to move out of the lab and became something a regular person could actually use.
And that brings us to our modern era, which is all powered by the microprocessor, an entire CPU on a single tiny chip. This is the tech that unlocked the personal computer. It gave us graphical interfaces, the mouse, handheld devices, and of course, when we linked all these powerful little machines together, it gave us the internet.
We are now living in the 5th generation, the era of AI, where our machines can learn, they can self-organize, and they can respond to our own voices. From a human with an abacus to a machine that understands what we say, it's been an absolutely astonishing journey. And that just leaves us with one final thought. What do you think the next big leap is going to be?